So shall I make a start?
Yes, go ahead.
Okay. Well, good evening, everyone. Thank you very much for inviting me to speak tonight. I want to talk to you about a fascinating world called Titan. Excuse me. Titan is, in my view, perhaps the most extraordinary world in the solar system because of the number of ways in which it resembles the Earth. And you'll see that as we go through the presentation. So let's begin with some fundamentals. This is an illustration which I'm sure you're all familiar with, and it is of the planets of the solar system. Titan is a moon of Saturn, and Saturn is, of course, one of the gas giants. You see here the water ice line, which lies between Mars, the outermost of the terrestrial planets, but inside of the orbits of the gas giants. And the significance of that is that objects that were formed beyond the ice line had water ice and other ices in the solar system as their primary building blocks, as well as, of course, the primordial gases within the solar nebula. And that meant that we ended up with the gas giants that we have. And in addition, it also means that we have a great number of moons of these planets, of the outer gas giant planets, that themselves are largely made up of water ice as well as rock. And that means that they are of lower density and they are sort of more fluid than the inner, more rockier moons and planets of the solar system. And this has significance for Titan, as I will describe. So if we look at the orbit of Titan, this is to scale the orbit of Titan, which is the orange blob on the right-hand side of the slide, and its orbit around Saturn, which you'll notice is quite markedly elliptical. And that means that the longitudinal gravitational tidal forces across Titan vary considerably, which means in turn that its gravitational field changes considerably as it orbits Saturn. And this allows any orbiting spacecraft to determine its internal structure, which I will describe later. The orbit of the moon, of Titan, around Saturn is just under 16 days. And it always keeps the same face towards Saturn in much the same way that our moon keeps the same face towards the Earth. And that means that if you were standing on Saturn and you were standing on the side of Titan, standing on Titan and you were standing on the side that faced Saturn, then Saturn would be a permanent presence in the sky. Although it might be a little tricky to see because Titan has a very extensive atmosphere, which is almost opaque to visible wavelengths. So when we think of sort of typical moons of the solar system, of which there are now known to be over 200, we probably think of moons a bit like these ones. So these are definitely not to scale, but on the far left you see our moon. In the middle we have I forget which the name of this moon is, I'm afraid, and we also have Phobos on the far right hand side. And so these three moons are heavily cratered. They tend to be grey. They may have lava flows on their surfaces or various sizes of craters, but they're very, very different. So Titan is actually very different to these typical kinds of moons that we're used to. Titan itself is unique in the solar system. It has a very strange, a very substantial atmosphere. This previous moon I should have mentioned is Mimas, which I've just remembered. So this is an image of Titan in visible wavelengths, and it was taken by the Cassini orbiter, the Cassini-Huygens mission to Saturn and Titan, which I'll describe in a moment. And it's fascinating because, in fact, you don't see a surface at all. It has a very opaque, invisible wavelengths atmosphere. And that atmosphere is chiefly made of nitrogen, but it also 94.2%, but it also comprises of methane, 5.7%, and trace amounts of hydrogen and many, many other molecules in its atmosphere, some sort of hydrocarbons and also other molecules such as carbon dioxide, argon, helium. It's very, very diverse in its chemical composition. Now, the reason why the atmosphere is opaque at visible wavelengths is because it contains a dense haze layer, very substantial haze layer, that scatters visible light and doesn't allow the surface to be visible in visible wavelengths. But it is visible, it is transparent in infrared wavelengths, as I will describe later. So it's completely different to any other moon in the solar system. And there is also an outer blue haze layer here as well, which is detached from the main orange haze layer that we see in this image. So it isn't really necessary for me to show you a picture of Saturn at this stage, but nevertheless, I just wanted to show it to you because it is so beautiful with its magnificent rings. So Titan is overwhelmingly dominates the moons of Saturn. It's far larger than any of the other moons, and indeed it is the second largest moon in the entire solar system, larger even than the planet Mercury. But it is the largest moon is in fact Ganymede of Jupiter. It is thought that it possibly formed after collisions with that there were a previous generation of moons around Saturn that collided with one another and then recoalesced. And it is thought that that is possibly how Titan and Rhea and Dione and Tethys and Iapetus came to be in the Saturn system. And this is backed up by the quite considerable ellipticity of the orbit, which I showed earlier. So to give you an idea of the size of Titan, this is the size of Titan compared to the Earth and the Moon. So considerably larger than the Moon, obviously considerably smaller than the Earth, as you would expect, but it is almost as large as the planet Mars. So Titan is, just based on its size alone, almost like a planet, really. It's a planet-like moon, and in particular with its substantial atmosphere. And that atmosphere is primarily nitrogen, as I mentioned, and that's another similarity that it has with the Earth, because the Earth and Titan are the only two moons in the solar system whose atmosphere is dominated by nitrogen. So this is a very potted timeline of the discovery and understanding of Titan. On the left here we have Christian Huygens, who's dressed rather magnificently and with his wig and his robe, staring rather knowingly at the camera. And he's there because Christian Huygens discovered Titan with his brother Constantine Titan in 1655, using one of the earliest telescopes. They were inspired by Galileo's discovery of the 4 moons of Jupiter in 1610, and went on to further develop their own build and develop their own telescope. It wasn't a Newtonian reflector, because Newton himself was only 13 years old at this date, 12 and a half, I think, at this date. So they went on to discover Titan, although they didn't name it Titan. It was later named Titan by John Herschel in 1847, the great John Herschel, son of William Herschel, who discovered the planet Uranus. Methane was detected in the atmosphere by the great Gerard Kuiper, after whom, of course, the Kuiper belt is named. He discovered that with a sort of primitive, by today's standard, spectroscope. And then subsequently, several spacecraft have bypassed Titan. Voyager detected nitrogen in the atmosphere and managed to determine its physical properties in 1980. And in 2004, the great Cassini-Huygens mission. Cassini was an orbiter of Saturn, as I will describe, and it carried a spacecraft called a lander called Huygens with it. And it arrived at the Saturnian system in 2004. And it went on to orbit that system for 13 years, finally being plunged into, at the end of its mission, into the atmosphere of Saturn. And shortly after arriving, about 6 months later, Cassini deployed the Huygens spacecraft, which landed on the surface of Titan. One of the most remarkable events that ever occurred in the history of space science. So much of the talk will be about the Cassini-Huygens mission, because this is the mission that has given us almost all of our knowledge about Titan, the vast majority of it, and has imaged and characterized the moon in wonderful detail. And as I mentioned, the spacecraft was actually launched in October 1997 and arrived in 2004, taking 7 years to arrive, and continued to orbit for 13 years. This was the trajectory that the Cassini-Huygens mission took. Ironically, in order to get to Saturn, you have to go in the wrong direction, essentially. You have to go towards the inner solar system, or you did on this trajectory, because Cassini-Huygens was such a massive spacecraft, and because Saturn is so far away, it cannot be taken there on its own fuel alone. The mass of the fuel required to do that without any assistance would be far too great. And so instead, various planetary flybys are used to borrow momentum or steal momentum from various planets in order to get the momentum necessary to reach Saturn. And so there were 2 Venus flybys in 1998 and 99, followed by an Earth flyby in August 99, which took it beyond to Jupiter's orbit and indeed bypassed Jupiter after 11.8 years, and finally arrived at Saturn on the 1st of July 2004. Now, one thinks of acceleration by propulsion as extremely important. Of course it is, but also it's very important to brake hard, and this is what Cassini had to do once it arrived at Saturn. It had to expend over half of its fuel, in fact, braking at Saturn in order to enter into Saturn's orbit, into orbit around Saturn, rather. So this is an image of the Cassini orbiter as it was on the ground before it was launched. And you can see the scale of it. It's nearly 7 meters high, and you can see the scale. There are various engineers working on it at the base of the image. You can see halfway up and facing the photographer almost is the Huygens lander, which is that circular hemispherical shaped spacecraft. And that's the lander that Cassini took with it to Saturn. And you see the enormous high gain antenna on the top, used for sending the data that it gathered back to Earth. And then there are numerous instruments underneath the high gain antenna that Cassini had. But of course, the Huygens lander had its own suite of instruments. So it's an enormous spacecraft, nearly 7 meters high and 4 meters wide. Very massive, over 2 metric tons. The Huygens lander itself was 349 kilograms. This mission, I think, cost billions of dollars. And an enormous amount of propellants, 3 tons, more than the orbiter itself, more than the entire spacecraft and orbiter itself. Half of which, as I mentioned, was used to brake once it got to Saturn, and the rest of it was used to perform the orbital maneuvers to not only orbit Saturn, but also to change its trajectory so that it could visit all the interesting objects in the Saturnian system over a 13-year period. So a breathtaking mission. And indeed, it ended up bypassing or flying by Titan a total of 126 times in that time. This is a close-up of the Huygens lander. You can see it separated into 2 components. The lander itself is the innermost circular spacecraft in the right-hand side of the 2 parts of the spacecraft in this image. And it too is bristling with instruments, both on its underside and its top side. We can look at the instruments here on the Huygens lander. They're almost all acronyms. The DWE is the descent Doppler wind experiment. The GCMS is the gas chromatograph and mass spectrometer. I'll describe these in a moment. The DISR is the descent imager and spectral radiometer. And the radar is a radar, which is used to take radargrams, radar images of the surface of Titan, and some of those images are absolutely breathtaking, but taken in radio wavelengths, not visible or ultraviolet wavelengths. On the underside, we have the SSP, which is the Surface Science Package, the ACP, the Aerosol and Paralyzer, Aerosol Collector and Paralyzer, I should say. So this is a graphic, not a photograph. Once it had arrived at the Saturn system, 6 months later, it deployed the Huygens lander to land on the surface of Titan, and it did so on Christmas Day in 2004. And it took 3 weeks for the Huygens lander to fall completely under free fall to enter Titan. And it was really extraordinary if you think about it. This is a vast distance from the Earth. So Saturn is, on average 1.4 billion kilometers from the Sun. And of course, Titan from that distance is a tiny, tiny pinprick in our telescopes. So the accuracy with which this had to be done was extraordinary. It took 3 weeks, as I mentioned, and all the time, of course, the whole system is rotating around Saturn, and it would have done so about 1.5 times in 3 weeks, or just about 1.25 orbits as Titan was orbiting Saturn. So I now have a few images which have been taken from an animation, in fact, of the descent of Huygens onto the surface of Titan. So here we have just a graphic. It's not exactly data from, it's not images from the actual Huygens lander, but it's just to begin with, it's a graphic. And it shows, it's meant to represent the probe entering the atmosphere at 25,000 kilometers per hour. And the heat shield on the probe slows it down to 500 kilometers an hour within a few minutes until it reaches 150 kilometers altitude. And then the main parachute opens, which reduces the speed to 300 kilometers an hour at 114 kilometers altitude. And this is followed by a stabilizer parachute, which allows a fast descent at first, then slows as Huygens enters a lower and denser part of the atmosphere down to 56 kilometers, and moving at still 140 kilometers per hour. And now we have one of the images that was taken by the Huygens spacecraft, and you can already see that it's extraordinary, and you can see that there are features which we can begin to recognize from Earth, from our experience on Earth. So in this image, Huygens is approaching a dark valley between bright hilly regions. And beyond the hills in the center of the image, on the left, you can see 2 parallel dark lines. And these are part of a vast system of dunes which surround the moon. There's a complicated system of drainage channels on the left, which are some hundreds of meters wide, and they're kilometers long and cut into the hillside. And these are probably the result of runoff of methane rain, because one of the most astonishing things about Titan is that it has liquids, not only in the atmosphere, but it has standing liquids of methane on the surface, which is in itself extraordinary. Another way in which it resembles the Earth and Titan are the only 2 objects in the solar system that we know of, and we're pretty sure, that have both standing bodies and liquids in the atmosphere. So an extraordinary system. Stereographic images show that the hills to the left are probably about 200 meters high, whereas features in the valley are tens of meters in height. So Huygens is about to land in this image, much closer to the surface, and it's going to land near a water ice outcropping ridge. But I'm going to reverse a little bit, and I'm going to show you a westward view of the descent from 32 kilometers. because this shows a better view of the drainage channels and what looks like an apparent shoreline on the right. In fact, it turns out in this case not to be a shoreline. So the area that Huygens lands in is in the darker regions. And it looks from here that that might be a shoreline and it might contain liquid methane. But in fact, on this particular occasion, that wasn't the case where it landed. So more dark lowlands appear, and there's a rough pitted hillside on the left. Spectra on the surface show that the bright areas are likely to be water ice, and the dark areas are a sort of class of, not really a class of chemicals, but a name given to very complicated molecules that haven't all been identified, called thiolins, and I'll go into that in a little bit more detail later. And now we have Tychons landing on the surface. And it's an astonishing image, as it would be, because of course it's the very first, or one of the very first images on an alien world, and this is what we, of course, all find tremendously exciting. The true aspect ratio of the image is this strip on the left-hand side. That's the true data that was taken, but it's been stretched for the benefit of the aspect ratio of a PowerPoint slide in the main image. And so what we see here, quite obviously, are rounded pebbles, and the roundness of those pebbles, or the roundedness of them, is important because it's almost certainly the case that there was once standing liquid here at this location, and that is why they're rounded, because of the flow of liquid has rounded and eroded these pebbles. They are probably not very large. Well, they aren't particularly large. They are between 1 and 2 meters in size. Some of them are no bigger than a fist, but the larger ones that we see here, between 1 and 2 meters. The surface was thought to be almost certainly saturated with liquid. So it was like landing on a soft, quite muddy surface. Neither rock, but not liquid either. Huygens was actually designed to land on either, amazingly, either a hard surface or a liquid surface, and it sort of landed on a transition between the two, which meant, of course, that it wasn't damaged when it landed. And we know what the hardness profile was of the surface because of the surface science package, which had a penetrometer on it, which decelerated in a certain way as the spacecraft pushed the penetrometer into the surface of Titan. And so it's thought that the pebbles are probably made of water ice with a sort of thiolin hydrocarbon coating around them, quite exotic. We can also see hills in the distance, and as the title of the image indicates, the shadow, which is to the sort of middle distance and to the right of the lander, was actually cast on the surface in this particular image. This is part of a series of images in an animation. When the Huygens landed, it actually vaporized some methane, and a dewdrop of methane was captured on one of the images as well. And this is some of the raw data before it was post-processed to get the image that you just saw. Quite Martian from the color. It reminds me of Mars, the sort of first Viking images, but smaller pebbles and more rounded. And this is because it's almost certainly a dried riverbed or dryish riverbed. So the high altitude science instrument measured the surface temperatures of minus 179 degrees centigrade, so incredibly cold. So although Titan resembles the Earth, of course it is far colder. It turns out that although Titan is 10 times further away approximately from us than the sun, than we are from the sun, and therefore receives 1%, its upper atmosphere receives 1% of the irradiation from the sun than we do, the atmosphere absorbs another 90% of that radiation. So the surface illumination and irradiation from the sun is only 0.1% of that of the Earth, and this partially explains why the temperature is so low. It's also low because there are two parts of the atmosphere. One has an anti-greenhouse effect and one has a greenhouse effect. I'll talk about that a bit later. So the high altitude science instrument and the Doppler wave experiment showed that there are considerable winds higher in the atmosphere of 430 kilometers per hour, 120 kilometers, but much, much lower at the surface. And this is a bit of a problem in explaining some of the surface features. The atmosphere also rotates considerably faster. The upper atmosphere rotates considerably faster than the surface does in a similar way to Venus. And that's because Venus and Titan have very substantial atmospheres, and it's also to do with the way the atmosphere circulates. The ACP, the aerosol collector and pyrolyzer, collected aerosols as liquids as Huygens descended through the atmosphere, and studied their composition, and it showed that they contain organic compounds, which is most interesting. I'll talk about the organic compounds a bit later. And the descent spectrometer, infrared radiometer, these measure the optical properties of the aerosols, and consistent with these of thiolin. So these instruments are able to take a spectrum and then establish what chemicals are responsible for that spectrum. Also using data on the ground, because these thiolin molecules can also be synthesized in laboratories, and therefore its spectrum is understood, as well as its optical properties. Now, several instruments imply that there is a methane cycle. So on the Earth, we have a water cycle where we have we have liquid water condensing in clouds in the atmosphere. Water vapor, I should say, condensing to form clouds which cause rain. The rain then falls, of course, to form lakes and rivers, which then evaporate into the atmosphere and completing the cycle. And an analogous process is happening on Titan, yet another way in which Titan resembles the Earth. The gas chromatograph and mass spectrometer and the descent imager and spectroradiometer detected a methane haze in the lower atmosphere. So it turns out that there are liquids and vapors of methane and ethane in the atmosphere. And this was suspected before they were discovered, because the properties of methane and ethane are known in great detail. And the conditions on Titan, are close to what's called the triple point of both of those. And that means that they can exist in vapor and liquid forms within very close conditions of temperature and pressure, and they do indeed so, and they indeed do so on Titan and in the atmosphere. The surface science package, which was the instrument that did experiments on the ground, found that the ground had a consistency of damp sand, as I mentioned before, and it's a mixture of ice chips, aerosols, and liquid methane. And as I also mentioned, the gas chromatograph and mass spectrometer measured a surge in methane as Huygens landed. So Huygens was invaluable because it gave us a trajectory through the atmosphere. And although Cassini did many measurements, there was nothing that, as an orbiter, of course, for years and for a much longer period, there is nothing like doing in situ measurements of a particular atmosphere and on the surface. And this slide compares the atmospheres of Earth and Titan. And you can see that there are similarities. So they both have nitrogen and argon in their atmospheres, for example. And they both have a cycle of water, as I mentioned. Earth, of course, has a water cycle, and Titan has a methane cycle. But you'll notice that the vertical scales are a factor of 10 greater for Titan than they are for the Earth. And this is because although Titan is, Titan is less massive than the Earth. This is the chief reason. It is also less dense, and therefore its gravitational field is far less strong than the Earth's, and therefore it has a more tenuous grip on its atmosphere. Nevertheless, the surface pressure of the atmosphere is 50% greater than on the Earth. It's about 47% greater, about 1.47 bar. and the mass of the atmosphere is 20% greater, even than the Earth, amazingly. So we have a moon, Titan, which astonishingly has a more massive atmosphere than the Earth. And as I said, the surface pressure is 50% greater, which is extraordinary. It's most unmoon-like, much more like everyone's idea, I expect, of a planet. This is a more detailed picture of the atmosphere of Titan, a cross section. It's not showing the entire atmosphere. We're only seeing the lower 140 kilometers of the atmosphere. The lower part is the troposphere, up to about 50 kilometers. So where the yellow line, which is the temperature profile, decreases from the surface. And it's that region of the atmosphere where all the weather is occurring. So there are clouds in the atmosphere of Titan. They're not constant, they're rather sporadic. There are quite significant ones that have been discovered on the poles, but more sporadic ones at lower altitudes, but they do exist. And they are responsible for raining out liquid methane, which falls and collects in lakes and seas, as we shall see. There is thought to be the passage of liquids from inside Titan, particularly liquid methane. Liquid methane must be being replenished within the atmosphere of Titan because it's being destroyed by sunlight in the upper atmosphere. And it would be destroyed if there were no methane being replenished into Titan's atmosphere, being pumped effectively into Titan's atmosphere, then it would have all long disappeared long ago in the solar system's history. So because of that, scientists have concluded that there must be some mechanism for replenishing methane within the atmosphere, and the only reasonable mechanism is from inside Titan itself. But there is relatively little direct evidence. There is thought to be cryovolcanism, which is the water equivalent of volcanoes that we find on Earth. Instead of magma, we have water and water ice, hot water ice that has been risen to a very high temperature and it escapes violently. But there is no real smoking gun. There's no strong, conclusive evidence for cryovolcanism yet. In addition, if we go higher in the atmosphere, there is this haze layer. And the haze layer is responsible for cooling the temperature. You can see the temperature as the altitude decreases, the temperature decreases because the layer scatters sunlight away. And then as the altitude descends, the temperature rises again until we hit the surface, to the surface. And that's because of methane. So methane is a greenhouse gas. And so the greenhouse gas warms the atmosphere in the lower parts, but the haze layer cools it in the upper regions. And if we go higher still, we have that thiolin haze, which is responsible for the orange color and impenetrable atmosphere to invisible wavelengths of the atmosphere. And in this slide, we've got more images of the atmosphere, cross sections through the atmosphere, but ones that discuss the chemistry, which is fascinating. So the chemistry on Titan is extremely rich, and to a chemist, it is undoubtedly has to be one of the most interesting objects in the solar system for this reason. So the vast majority of the atmosphere is made of nitrogen and methane, but these molecules are readily broken down by by photons from the sun. So in the upper part of both images, you see photons from the sun coming from the upper left, but also there are energetic particles trapped in the magnetosphere of Saturn, which are also impacting the methane and the nitrogen in the upper atmosphere. And this causes two processes to occur. Dissociation, which breaks apart the molecules by photolysis. This is what the photons are chiefly doing, which is a neutral process. So the result is that the methane and nitrogen are split apart, and then the atoms of both those molecules recombine in all sorts of combinations to produce the molecules, examples of which you see here: ethene, ethene, ethane, and hydrogen cyanide, but many others as well. And the energetic particles are charged particles, which cause very large charged molecules to build up, as you see under the, and some of them are listed under the ionization label on the right-hand side. And then further chemistry produces even more complicated organic molecules further down in the atmosphere. So you may, some of you remember chemistry from school, perhaps. Benzene is a familiar laboratory molecule, a ring, and this is a ringed molecule. And there are other complex organic molecules present as well, things like polycyclic aromatic hydrocarbons, thought to be important for life. And then there are, even further down, very massive, surprisingly massive molecules. So the 20 to 8,000 Da, that stands for Daltons, and it's an indication of how enormous these molecules are, because hydrogen has a Dalton number of 1, carbon 4, oxygen 6, and so on. And so 8,000 is an extremely large molecule. And the result at the very bottom is the precipitation from the atmosphere of a mixture of molecules that have been dubbed thiolins by the great Carl Sagan in 1979 and his co-worker. And in that paper, they say that they've managed to synthesize molecules that are very similar in color and properties to those found on Titan. But it's very difficult for them to establish what they are. But they're definitely long chains. They're definitely not polymers, but they are long chains and very difficult to analyze. And they dubbed them thiolins. One nickname was star-tar, but they decided against that and they called it thiolins. And these thiolins are also found on comets. We now think they're found from the Horizon mission to be found on the surface of Pluto. And so this is what we find in the haze of Titan and also on the surface. Now, there is thought to be geological activity as well, and that means, and evidence for that is not only the virtual certainty that methane is being replenished, but direct evidence is from the discovery of an isotope of argon. So you may remember that isotopes are kind of types of elements. So an element is distinguished by the number of protons in its nucleus, but a given element may vary in the number of neutrons. And so argon has 40 neutrons and protons. I think it has 18 protons in its nucleus, and argon 40 has therefore 22 neutrons. But the important point is that 40 argon only comes from an isotope of potassium called 40 potassium, and that only comes from radioactive decay of potassium-40. This is a well-established process that occurs in the Earth. And what this is evidence of, therefore, is that there is transport of gases from, because argon is a gas, from the inside of Titan into the atmosphere of Titan, and therefore evidence of geological activity, which could be cryovolcanism, but we don't know. And also, interestingly, the ratio of 2 different isotopes of these time of nitrogen is an important indicator as to where the nitrogen in the atmosphere may come from. And it turns out that it's similar to the ratio of those 2 isotopes in cometary ammonia. And so what this means is that the building blocks of Titan almost certainly came from cometary material and were not, therefore, likely to be accumulated from nitrogen in the nebula surrounding Saturn, so that the atmosphere is primordial. So not only did Huygens have the instruments that I described, but Cassini did as well. And with those instruments, it made some extraordinary discoveries on Titan's surface. And made important conclusions about what exists inside Titan as well. So the imaging science subsystem consisted of a wide and a narrow angle camera that mainly looked in visible light. So that would not have been able to penetrate the atmosphere of Titan. But nevertheless, it did take many beautiful images of Titan as well as Saturn and its rings and moons. And I thoroughly encourage you to go to the Cassini website to look at these images, because if you haven't done also already, because they are breathtaking. Now, importantly, Cassini had a radar, imaginatively called radar, and this was able to, was an active instrument. It sends pulses of radio waves towards Titan, where they are reflected off the surface. And many of these, I believe, were actually picked up by the Earth, astonishingly, for analysis, as well as Cassini itself. I didn't realize that until recently. Anyway, you will see some breathtaking images, if that's the right word, or radargrams from the radar instrument shortly. It's able to determine the topography of the surface and to understand, therefore, what the geological features might be. It also had a visual and infrared mapping spectrometer. Spectrometry, as I'm sure you know, is one of the most powerful techniques in all of science, and it is able to determine the altitude and thicknesses of the clouds and hazes on Titan, and possibly did discover an ice volcano, although, as I mentioned, that's not conclusive. There's also an ultraviolet spectrometer used to determine the composition and aerosol particle content, as well as the temperature of the atmosphere. A Cassini plasma spectrometer, which can look for charged particles. And this is extremely important because it was able to detect not only negatively charged particles that I mentioned in the atmosphere, but also how massive they are, which is important for its chemistry, understanding the chemistry. And also a spectrometer that looks at ions and neutral species within the atmosphere. So in summary, one of the main findings, well, radar showed the presence of seas and lakes, confirming what was previously suspected, that there are lakes and seas on the surface of Titan. A really astonishing discovery, and an extremely rare one in the solar system, the Earth being the only other case. The visual infrared and mapping spectrometer also imaged glints of light reflected off the lakes, so that was rather beautiful. And the imaging science subsystem detected huge dunes, hundreds of meters high and 1 to 2 kilometers wide, that actually encircle the moon, made of ice and coated with hydrocarbons. And it also discovered south polar clouds composed of methane. And the high gain radio antenna. Now, this high gain radio antenna didn't bounce radio waves off Titan. What it did is carrier wave only was picked up by the Deep Space Network ground stations on Earth. And basically the refraction, how the behavior of that carrier signal, the Doppler signal, and how it is refracted in the atmosphere, allows scientists to establish what the trajectory of Cassini orbiter is each time it bypasses Titan. And that in turn allows the gravitational field to be established. And that itself allows the models of the internal constituents of Titan to be validated or not validated. And the most plausible model is that Titan also has a global subsurface ocean of liquid water, which is another astonishing find. So this is an image of Titan. Titan is not green. This is an infrared image. But what it shows in a rather wonderful way is that at the top left-hand corner, we see a glint of light of one of the lakes of Titan. And I think it was the lake Youngpo Lacus, which I'll describe in a moment. So the findings from the radar instrument is that there are lakes in the polar regions, and the lakes in the northern hemisphere are filled with methane. Some of them are surprisingly deep, over 100 meters deep. And what's also interesting is that they tend to be perched on top of hills, hundreds of meters above the seas. So there are seas as well. There are 3 large seas, and these have the same sea level. So that indicates that there is probably, almost certainly, underground communication between them. A bit like if you imagine a YouTube, not YouTube the website, but a YouTube in the laboratory. If you fill that with water, then both the meniscuses in each of the tubes will, in equilibrium, be of the same height, and it's similar. And that's because, of course, they're connected, and a similar process is thought to be the case for the northern seas. But interestingly, there is a large lake in the south, but that has a different composition. It has a roughly equal mixture of ethane and methane. And the contrast between the north and the south is almost certainly because of seasonal variations. And when Cassini first arrived, that's a shame. When Cassini first arrived, Titan was in the northern hemisphere, was in winter, but it transitioned into the seasons began to change during the latter part of the mission. So this is a two polar projections of Titan, illustrating the distribution of lakes and seas. On the left, we have the North Pole, and in the upper left and the upper left of the image, we see the outlines of three substantial seas. Punga Mare, Kraken Mare is the largest, separated by a narrow region which is amusingly called the throat of Kraken. The second largest is Ligaya Mare, I think I'm pronouncing these correctly, and then the smaller one is Punga Mare. All of them pretty substantial. Also, in the bottom right, and to the right and the bottom right in particular of the same, on the left-hand side, are numerous smaller lakes, and more numerous than in the southern hemisphere. On the southern hemisphere on the right, we see a distribution of lakes, and a very large lake, Ontario Lake. None of these are classified as seas. And this is another picture. This is of a glint of Yingpo Lakes, but with the sun behind, so that we're seeing here that the far side, the dark side, if you like, or the far side from the sun. And this geometry was used so that you did get the angle required from the sun to try and get a glint. I think this was sought after for many years because it was predicted, and finally it was achieved in 2009. So this is not an optical image. This is a radargram taken by the radar instrument on Cassini. But you can see that immediately that it has a very high resolution, which is astonishing. For an orbiting radar instrument 1 billion kilometers away, to achieve this kind of resolution is astonishing. And there are some even more astonishing images to come. But it shows effectively the three seas that I showed earlier. And this is, again, this is at Titan's North Pole. There are thought to be lakes near the equator, but these are probably formed from underground aquifers, not rain, because the temperature is likely to be too high. So this is one of the seas. This is Ligaya Mare, the second largest of the seas. Nevertheless, it has a very large surface area, 147,000 kilometers squared. It's very deep, more than 200 meters deep, and an average depth of only 50 meters. It's huge. It's larger than Lake Superior. And I ought to mention that these are all filled with methane and ethane, not liquid water, but also that therefore the total inventory of hydrocarbons on Titan vastly exceeds that of the Earth by as much as 100 times, I believe. So this is the same. This is also Ligaya Mare. So I flick back and then flick to this one. But the difference in this image, is that there is a radargram in the bottom right-hand corner. So this is the use of the radar instrument in a different mode, where it's bouncing. Instead of forming an image, it's actually establishing the distance of the various photons, radar pulses of electromagnetic radiation that have been sent and are reflected back to the orbiter and to Earth. And effectively, this radargram that you see on the bottom right, in the upper panel, you see a thick horizontal line. That horizontal line is the reflection of the radio waves from the surface of the lake along the red dashed line that you see in the image across the lake. But the lower curve, more astonishingly, is the actual profile of the bottom of the lake. So not only are we imaging these lakes in great resolution, but we are also establishing the profile of the bottoms of these lakes, which to me is just extraordinary, that human beings are capable of doing such an experiment and getting these results is really, for me, very inspiring. In the lower panel, you see the same cross-section, just at a different orientation to the main image. Now, this is rather amusing, actually, this phenomenon. This is the phenomenon of magic islands, and it's been seen on Ligaya Mare. So what you see in the main image is Ligaya Mare, and there is an inset, and that inset image is also reproduced over in 4 snapshots on the left of the main image over 4 different intervals, separated by, in total, by quite a margin, 7.5 years. But what is clear from those 4 images, the smaller images on the left, is that there is a feature in the upper left of each one of them that wasn't present in the first image, is definitely present in the second, is fading from the third, and has disappeared in the lower image. And this has been dubbed a magic island. And there is a theory as to why this is happening. It is not thought to be because literally a solid island is appearing and disappearing. It is instead thought to be the presence of nitrogen bubbles within Ligaya Mare. And the theory goes something like this, that the nitrogen atmosphere is dissolved within the lake. And the lake also contains ethane and methane. The methane floats on the top and the ethane is underneath. Broadly speaking, there's a transition of concentration of both of them, but nevertheless, broadly speaking, that's the case. The nitrogen, the upper methane layer with dissolved nitrogen is by some process, not properly understood, hypothesized to be forced downwards to mix with the lower layers, but in the process to cause the nitrogen to separate out because of the higher pressures lower in the lake, which causes the nitrogen to then bubble up to the surface. And it's the bubbles of nitrogen that are thought to cause the magic island. Because remember, this is not a visual image, this is a radargram. And it is bubbles, the surface of the bubbles are highly opaque to radio waves. And so this may explain the magic island, and it may explain also why it is transient. It's not clear, I suppose, why it's not happening all the time, but we don't fully understand the process by which it may be triggered. So that's not unreasonable. That's an explanation, and I really love that explanation, because the idea that we've not only characterized the lakes, we've discovered them and we've characterized them to some extent, but we've also think we've discovered bubbles in them, something I don't think anybody would have ever dreamt of. I think that comes under the category of you couldn't make it up. So this is another lake. This is Kraken Mare. This is only a tiny bit of it, but you can see again the astonishing resolution, really beautiful image. It has a very large surface area, 500,000 kilometers squared, and a maximum depth of 160 meters. There is some evidence, it's not particularly conclusive, I don't think, but that it has small waves, but absolutely tiny rippling waves, 1.5 centimeters high. Even waves that tiny, there is difficulty explaining how they could have formed, because the wind isn't thought to be sufficient. But nevertheless, they are thought to have been discovered. Basically due to that there is a surface roughness, but broadly speaking, each of the lakes would actually be much more like a mirror and would unlikely to be particularly rough, because of the waves are known to be no more than just a centimetre high. This is Ontario Lake, as a footprint-shaped lake in the southern hemisphere. And this is quite extraordinary. It's made of methane and ethane, liquid methane and ethane, as I mentioned before. But despite the very large surface area, it is extremely shallow for its size. It would be very surprising to have a similar shallow lake on the Earth for that size, although there is one in Ethiopia, I believe. So moving on from the lakes, there are other features which remind us of the Earth. This is what you're seeing here in the main image is an image of dunes in the rather wonderfully named region Shangri-La. And you can see many parallel lines of these dunes. And these dunes encircle the globe. I'll show you global geological image in a moment. On the right-hand side, we can see two sets of dunes for comparison. Sorry, so the upper right is one from Earth, from the Namib Desert for comparison. But on the right, there's the sort of lower, sort of higher, a more wide area view of the dunes on Titan in the so-called Belet region. And what I love about this is that it really shows the parallel lines very clearly. And the obstructions in the dunes are not clouds, they are physical obstructions within the dunes. And you can see the rather wonderful way in which the dunes have sculpted themselves around these surface features, which I think is very beautiful. The way that these dunes have been formed is a bit of a puzzle. The surface winds during most of the cycle of Titan around Saturn, and as Saturn orbits the Sun, are not thought to be powerful enough. But the seasons are driven by Saturn's orbit around the Sun. And as Saturn transitions from one season to the next, and therefore Titan does as well, during its equinox, that is thought to create storms, and those storms will produce downdrafts. And those downdrafts can be up to 10 kilometers per second, 10 meters per second, and it's thought that these are powerful enough to sculpt the dunes that we see. There are also labyrinthine structure. I can only describe it as a bit like crazy paving, but I can't really describe it better than the images that you see here. So on the left we have an image from Titan, and we have a similar image, although at a different scale, of labyrinth features on Earth, and yet this is yet another way in which Titan resembles the Earth. So this is the first global geological map which summarizes the findings from the Cassini orbiter. And it's obviously in false color, but nevertheless, it's illustrating the main geological features. So the purple are the dunes which surround the equator. In sort of a sandy colored, in a reddish color, are craters. Now, craters are few and far between, far fewer than you would expect for a moon, and that doesn't have an atmosphere or liquids, such as, say, our moon or Mimas, or any of the other moons that we find orbiting, or any of the moons that orbit Titan. And this is because Titan has an enormous atmosphere, and that would cause larger objects to break up more readily. And so far fewer objects are hitting the surface. And it's also because of erosion, because of liquids on the surface, undoubtedly, and albeit light winds, undoubtedly have erosive effects on craters as well. And that's why relatively very few are seen compared to other similar moons. The lakes in blue are illustrated in the polar regions, which I described before. The orange are hummocky regions. The purple, sort of light purple, are labyrinths. And the majority of the surface in green, light green, are plains. And these are the most beautiful images, global images that we have of Titan. And these have been sewn together by mosaics. And we were talking about mosaics earlier. So this will be a challenge for any software, but NASA spent a great deal of time sewing together the images taken by the Cassini orbiter, because of course they were all taken under different lighting conditions and different distances to produce these wonderful images. and the orange are the dunes, and the different colours are due to the different chemical compositions of the various surface features, particularly ices as well. So this is a model, and it is a model because the properties that an orbiter has no mechanism to directly see the internal structure. Nevertheless, this picture is built up by credible models of the interior of Titan based upon, first of all, the likely components that are found that we know are orbiting Saturn, particularly rock and water, of course. And also we know the composition, of course, of the atmosphere, but also an understanding of what the pressures will be and the temperatures are likely to be within Titan. That can be established because we know the total mass. But by using the high gain antenna experiment, which, if you remember, was a carrier wave from Titan to the Earth, and because that carrier was bent, sorry, not by refraction, but by the gravitational field due to Einstein's general theory of relativity, how that varied allowed the gravitational potential field to be mapped for Titan at different parts of its orbit. And this allowed the model to be pinned down, and in particular, the moment of inertia to be established. And it turns out that internal models of Titan are sensitive to the moment of inertia. So models that are continuous, that are not differentiated, have higher moments of inertia than ones that are differentiated. And if you put all of these measurements and theory together, it's thought that the most plausible model is this one, with a hydrosilicate core, i.e. a core which has a great deal of water inside it, followed by high pressure ice-6 shells. So ice has, I think it has 12 different forms, and this is ice-6 form. On the outer part of that, you have the global subsurface ocean. And beyond that, there is a decoupled outer shell. And finally, we have the organic rich atmosphere and surface that I mentioned before. Now, other evidence that I neglected to mention is that there is evidence, direct evidence, that the outer layers of Titan are disconnected from the inner layers. In other words, the outer surface is not behaving as if it were rigidly connected to the internal surface. So this lends credence to the idea, or adds credence to the idea, that there is an ocean. In a similar way, we see the similar effect on Europa. So even, this is yet another testament, I think, to the bringing together of science, of theory and observation. So what of the future? So in the near future, there is an upcoming mission which is highly likely to go ahead. And that's because this mission, the Dragonfly mission, belongs to a series of other missions that have indeed already flown, because they belong to NASA's New Frontiers program. And these other missions are OSIRIS-REx, which is looking at, currently, I think, orbiting the Bennu asteroid. I believe it's called Bennu. Also the New Horizons spacecraft, which of course bypassed Pluto in 2015, is on its way, I think, onto another object. And also the current Juno mission, which is orbiting Jupiter. And therefore, I think this Dragonfly mission, which is a selected mission from other previous missions which were previously rejected, very likely to go ahead, and it is anticipated to launch in 2026. And the payload, or the main component, is this object, this flying drone, if you like, that's the word I'm looking for, drone, which has wings, and it can characterize the atmosphere as it flies through it, but also it can land on solid surface, and I think liquid surface too. and then characterize it there and then fly off and go somewhere else, because no matter how wonderful Huygens measurements were, they were only a single trajectory. And we know, of course, that real worlds are much more complicated and need a lot of measurements to more properly characterize them. But of course, science and engineering progress in stages. Cassini-Huygens, this mission would definitely not be possible were it not for the science and the engineering learned from the Cassini mission. But what of the far future? Well, in the far future, interesting things are likely to happen. Well, will certainly happen, because the sun, as I'm sure you know, will not remain as we are familiar with it forever. It has a finite supply of hydrogen in its core, which it burns, in inverted commas, via nuclear fusion to helium, which of course produces the heat, the light, the radiation that we require to exist. And it's been doing this for 5.5 billion years, 5 billion years. And it's middle-aged, and it will live for another 5 billion. That hydrogen will sustain it in its core for 5 billion years. But the hydrogen is finite, and in the core, once it runs out, the core will begin to compress and the temperature will rise. And this will cause what is called shell hydrogen burning, which exists at a much higher temperature. And this is more energetic than the fusion reactions in the core. And the result is that it pushes the atmosphere, the outer envelope of the sun, out to a vast extent. You can see the sun there as a tiny spot in the inset, compared to the sun as it will become as a red giant, thought to have a diameter of 2 astronomical units. So its outer surface will approximately be at the orbit of Earth. And the Earth may well be incinerated as a result, will certainly be incinerated and may in fact be swallowed by the sun. The consequence of this is that the outer atmosphere will become, the outer solar system will become warmer than it is currently. And it's thought that the atmosphere, the temperature around Titan may well rise to minus 80 degrees centigrade. Now, Titan is made largely, as a large component is water, and the mountains and the surface, many of the surface features are chiefly water internally. And these may well melt because they are thought to be combined with ammonia, as I mentioned earlier, which is the source of the nitrogen in the atmosphere. And this means that their melting point is much lower than would be expected for pure water. And so they may well begin to melt. And then you suddenly have an organic chemistry combined with water. And those conditions are exactly those, or similar to those that existed on the early Earth, which of course gave rise to life. So this is tremendously interesting. Many of the organic molecules, such as the PAHs, are known to be important to life on Earth that already exist. And so it's just possible that life may form on Titan. Of course, we have no way of concluding that. The origin of life on Earth is a mystery, and it's an immensely complex subject, but it is rather wonderful to think that that might happen. Albeit briefly, because of course the sun will not retain that state for long. The sun will shed its outer layers and it will begin to cool to become a white dwarf. And therefore the temperatures will almost certainly lower again. So this is my final slide of my presentation, and it's a rather romantic image. And I've done this because I want to remind you just how much Titan resembles the Earth. So we have these, in the upper right, you have the sun, and the sun's light is glinting on the very lightly rough surface of a foreground lake in this illustration. Most definitely not a photograph, but an illustration, but based upon science. And on the left-hand side and in the distance, you have these hummocky and hilly regions, very familiar to us. Admittedly, there is this orange haze, but it sometimes occurs on Earth as well. One thinks of Death Valley, for example. And in the sky, I'm not certain that you would be able to see Saturn because of the scattering of the atmosphere, but it's rather wonderful to think that you might. And if you could, it would stay there if you were on the side that faced Saturn. As I mentioned before, it will stay there permanently in the sky. And I think this image not only has a sort of an emotional value, but it also is a testament really to science, and it's a testament to engineering as well, and what human beings are capable of when they are organized properly and determined enough, and of course properly funded to produce this extraordinary science and extraordinary understanding of this amazing world that we call Titan. So thank you very much.
Brian, thank you for an absolutely fascinating talk. Just amazing that how much we can learn from so far away with a bucket full of instruments hanging around there for a few years. So quite stunning, and thank you for bringing that to life for us.
It's a pleasure. I also point out that poor Trevor has listened to this presentation for the 3rd time. Which I think is a record. It's the 5th time I've given it. He's been present at 3 of them. I also wanted to say that he was very kind, not only in his introduction, but that I was originally introduced as Dr. Brian Skidmore, but I in fact do not have a PhD. I want to make that clear. But Trevor has very kindly lent me his PhD for the duration of this presentation. And it is my intention to get a PhD one day, but it's been very nice to sort of try before I buy and to get that sort of rather lovely feeling of having a PhD. So yeah, if anybody wants a prescription, let me know.
Very worthy, Brian. Thank you as well. We have got time for some questions if there are any. I think Alan put a couple on the chat screen. Alan, do you want to voice those rather than me read them out, if Alan's still with us?
Oh, I can't see them. I can see the chat screen, but I can't see those questions.
That's interesting. I can't even see Alan now.
Missing Alan, we're missing the chat screen.
Oh, is he there? Oh, yes, he is still there. Yes.
Yeah, no, it was a couple of questions.
Yeah.
The first one was the names, Xanadu and various other ones. Have they had approval from the IAU yet? I presume not. They'll probably approve Xanadu and things like that.
Well, my assumption was that they have, but it sounds like that you're more aware of the approval process for Titan than I am. They are established names. They appear in textbooks. Okay. and websites. So I think they are IAU names. Wonderful that they are. Of course, the IAU is not averse to wonderful names. We have all the names of the craters, the female craters on Venus as well, which are wonderful names. And the moons of Uranus are also wonderful. So I think IAU does have a rather wonderful sense of imagination, and I think they almost certainly are approved. Does anybody know better than me?
Yeah, hello.
Hello, I can hear you.
Yes, my name's Diana Chalice. I'm a former planetary scientist from the USA, and yes, there's an entire massive process that goes into this from the planetary side of things, and there are a number of committees. And if anybody wants the websites that will list every single feature on every single planet we've got, I can provide that for you. It's the Gazetteer of Planetary Nomenclature.
Wow, you might get more than you bargained for, but that is
yes,
that's the definitive answer. But do you know, Diana, whether these particular ones like Xanadu and Shangri-La have been approved? Do you
yeah.
They have. I was okay. So I wasn't far. I was right then. That's a relief.
They wouldn't be on the maps by now if they weren't. They're often listed as tentative names until the process goes through, and we're far enough along that yeah, they've gone through. In fact, as soon as something weird shows up, there's a nomenclature structure is agreed even beforehand, even as the mission is ongoing, and we have a large numbers of all Latin names for things already, but I don't know nearly enough about Cassini, but I was around for Galileo and the fun and games that involved with the Galileo nomenclature, and we'd agreed on what Io and Europa and Ganymede and so on were what categories there were going to be even before the thing arrived. It's just that once it gets there, the surprises occur.
I know there was a case with New Horizons and the Sputnik Planum, I think, in the actual fact, because they thought it was a mountain and it was depression in the end, so they had to change it. They were referring to a Sputnik Planum, I think, to start with, and they had to change it subsequently because it was found to be.
Well, they broke with protocol there, and everybody was very upset.
Do you have another question?
Was that with us? Thank you, Diana.
Yes, I also have a number of questions, but I didn't know about the chat thing, so let me.
No, it's okay. Well, you can voice them if you wish, but I think Alan had a supplementary or a second question about whether the core rotates at a different rate to the outer surface.
That was exactly right, because Brian, you said that the core and the outer surface were separate. I didn't know quite whether they rotated at different speeds.
Yeah, so there is a separation, and I think there's probably some oscillation going on as I'm not 100% sure, but as Titan rotates around Saturn, there may be the displacement between the two sort of oscillates rather than being a continuous drift. I'm not 100% sure about that, but it's established because of the difference visually and the gravitational field. That's how it's established.
Okay.
If that helps.
Okay.
I have a question for Brian.
Yeah, go ahead, John.
Does Titan have a magnetic field? And if not, how does it retain its atmosphere against the solar erosion?
So Titan does not have a detected magnetic field, and this is almost certainly because it doesn't have a molten iron or a molten core of, a ferromagnetic element such as iron or nickel. What it does do is it orbits almost continuously within the magnetosphere of Saturn.
Yeah,
okay?
Makes sense.
So that is why it's protected. But I understand that when it pokes out of the magnetosphere of Saturn, that it carries some of the magnetic field with it to an extent. I don't understand that, I have to confess. But I hope that answers the question.
Yes, thanks. Yep.
No problem.
Any other questions?
Yes, I've got a question.
Keith.
If I may, yes.
Sounds like Keith.
Of course. Yeah.
It is, yes. With its neighbour Saturn, obviously a rather large planet with huge gravitational influence, is Titan in a fairly secure orbit?
Well, I mean, in the sense that, if the largeness of the mass of Saturn itself doesn't influence the stability of the orbit, because if, for example, Titan and Saturn were alone in the solar system and there were no other objects possibly causing a perturbation, then simply because Titan is massive doesn't change the stability of that system. But nevertheless, I believe it is stable to the extent that can be foreseen, but that doesn't mean that it couldn't be perturbed by an incoming object, for example, from the Oort cloud. Although it is very massive, typical objects from the Oort cloud are vastly smaller than Titan. It's possible it could be perturbed by the presence of the other moons. Nevertheless, there is a substantial distance between Titan and the other moons. It's not as if it's one of the shepherd moons in the rings, for example. I think it is pretty stable for the foreseeable future. I've not read anything that suggests that it may be unstable, or any reason to believe it's less stable than any of the other objects. But it probably did form from the collision, from previous violent events, previous collisions between a previous generation of moons. So violence within the Saturnian, also the Jovian system, is thought to occur periodically. But that might be during the period of heavy bombardment when there is much more chaos in the solar system than is currently the case. Does that help?
Yes, thank you.
Okay.
Can I ask about the mare?
Please do, yes.
Go ahead.
Well, loads of questions about those. Those are brilliant.
Well, I'm not sure that I'll try my best to help you, but
all right. The three largest mare. It's fascinating that they're all at an even level, and the suggestion that they're being equalised from below.
Yes.
However, I see on the images that there appear to be a number of drainage channels. So I'm trying to equate what look like rain and runoff features with to something that is being sported from below.
So what's the contradiction you're thinking of? I'm trying to understand why there's a conflict there.
We only have two worlds that have surface liquids, Titan and Earth.
Yeah.
And on Earth, the even sea level is created by a constant water cycle with runoff from the land to the oceans.
Yes. Oh, I see I think I see what you're saying. Well, I think.
So I'm trying to.
So you're trying to understand why I said that internal communication must be responsible. Is that what you mean?
Yeah, but yet we see runoff features.
So you see, runoff features because it's raining. There is topography. The methane rain is running down.
And
the edges of hills, and I think that's separate from understanding why the seas have a common sea level. So, I mean, I understand that seas on the Earth, I'm certainly not an expert on seas on the Earth, there is a variation in the sea level there. I mean, not the oceans, but certainly in the larger seas, there is difference in sea levels. If they're not connected, they will not be in hydrostatic equilibrium. Do you see what I mean?
Yeah. Okay. So you're saying there are two processes going on simultaneously.
Yeah. So I'm saying, yes, there's runoff, but it's not substantial to equalize to make them at the same level. It can only really be because they're connected underneath. Sorry.
Yeah. It leads to my other question: was that if they are coming from the underneath, and it's is there any those glints coming off them? Could that be some kind of form of outgassing from below?
Well, I think the glints are simply light being reflected. So the glints are light being reflected. It's not thought, and it's very much the surface. It's not thought to be caused by an internal process of drainage or liquid movement. I've not heard that described. I've only heard the glints being described as a reflection off the surface and possibly
because I was wondering about a chemical change caused by outgassing and then ending up with a different, causing a different bounce signal.
Oh, I see. Well, I mean, I think the outgassing would have to be pretty substantial because many of the lakes are pretty deep, although some of them, of course, are very shallow. But we're not seeing. The thing is that actually the lakes and the lakes are extremely smooth. I mean, we really struggle to see surface roughness on them, and the surface waves are very, very slight, and it's thought to be down likely due to wind rather than considerable outgassing in the lakes themselves. So there is outgassing. There is evidence for outgassing from the Argonne 40, and that will be from the land, and probably is under the lakes as well. I see no reason why not, but it will be under considerable pressure as well. If you think about it, the hydrocarbons, I suppose, a similar density to water. Some of the depths are between tens or even hundreds of meters, so a considerable pressure at the bottom of many of these lakes and seas. I suppose the outgassing would be bubbles, wouldn't it? That might sort of float to the surface. That's an interesting idea. I haven't heard that described. But one thing I do think is that the outgassing of the methane is similar to the composition of the lakes themselves. It's not substantially lighter. If the gases were of a much lower molecular weight than the constituents of the lake, then you might see many more bubbles on the surface, if you see what I mean.
kind of a steaming effect.
Yes, you know, you'd have, you know, if you had a very high molecular weight lake, then you could have, and you had very light bubbles, and you could imagine that the sort of hydrostatic pressure would force them to the top very quickly, like, you know, like opening a can of soda or something. But
cappuccino.
yeah, exactly. But I don't think, I've not read that that's occurring, but I think it's a great idea, and it never occurred to me. So
I was also wondering about if a similar thing when you were talking about bubbles in the Mystery Island.
yes, the Magic Island, yeah.
Yeah, the Magic Island. That's a brilliant term.
That's a brilliant term.
I was looking at that, going, have we got a Titan iceberg on our hands?
Well, I think
Winter.
let me see, what would you need? I don't think you could eliminate that. Actually, I've not seen, I don't know if they were visible in the infrared images. You know,
why not have a methane tholin iceberg?
Yeah, why not? Why not?
And it, like icebergs on Earth, they'd be full of air bubbles, which would make it brighter on the radar bounce.
Yeah, I mean, the methane is mainly in liquid and vapor form, so I don't know if it would be. And the tholins come from the atmosphere, so they rain down from above. So I guess they could accumulate. I mean, in my mind, the perimeters of the lakes are chiefly water mixed with frozen water mixed with ammonia, with a thiolin covering, and therefore you could have an iceberg literally made of water ice, but water ice behaves like rock.
Yeah, this is why I was thinking of like a methane clathrate berg.
Yeah, but the berg, that means solid methane, and we don't get solid methane. We get sort of coatings of. It's near its triple point, but I think I don't think you get a huge amount, a very substantial body of solid methane accumulating. You see what I mean? But I think it's perfectly possible as well. But I haven't read that. But it's perfectly possible. I like the nitrogen bubble idea. That really appealed. Maybe I'm just biased because I like nitrogen bubbles. But I think it's a perfectly plausible idea.
Right. Thank you.
Okay. Any other questions?
Yeah, I have a question related to the runoffs that look like rivers. What's the mechanism for the erosion? Do we know?
Well, the runoff, it rains methane onto the surface, so it will be the friction of the liquid methane against the solid surface, which will cause erosion.
Will that lead to particles being transported into the lakes?
I think that must be plausible. I would have thought so. Yeah, I don't think we can demonstrate that though. That's the thing.
We might actually, because do you remember the last picture from Huygens?
Mm.
And it showed the rocks.
Yes.
And
okay. Yes, fair enough.
How they were smoothed. And
yes.
The only way that we know to get smoothing like that is from surface water erosion.
Yes. So yes, that's right, and that's what I was saying on that image. In fact, that the roundness of those rocks. But what I was thinking of is the transport of particles from the runoff on the hills down towards the lakes, and actually having tangible evidence for it occurring. So I think there is evidence that it has occurred on that image. But what I was thinking of, could we somehow demonstrate that it's actually happening in that runoff? And that's what I was thinking when I said it's difficult. It would be difficult to get. I didn't think it would be possible to get evidence. But of course, you're absolutely right that there is very clear signs of erosion in that image. Yeah.
And those eroded particles have to go somewhere.
Yeah, exactly. It's very much like a riverbed, on Earth.
Thank you.
If I may ask a question there, Brian.
Yeah, sure.
Interestingly, looking at the orbital path that Titan takes,
yes.
I would, and your earlier reference about the methane that's in the atmosphere must be renewed from below. That's otherwise it would be lost lost to chemical action.
Mm.
I would have assumed that there was quite a lot of tidal elasticity induced by the orbit as
Absolutely.
it goes around Saturn, which would
Yes.
potentially give you your source of the release of methane.
Yes,
from-
exactly. Yes, that's very much the case. Yeah, yeah, very much.
Okay.
There's considerable elasticity because of the softness of the material in which
Indeed, yeah.
Titan is made compared to the terrestrial planets, and much lower density. Yeah.
Which could also be the source of potentially giving you your cryothermal effects in
Exactly.
volcanism.
Yeah. Yes, exactly. Like Io is a very extreme example of that, of course.
Oh yes, yes.
Yeah, I totally agree. That must be a source of energy to produce the outgassing. But there is certainly outgassing. I think that must be happening, and
Okay.
there is evidence from the potassium argon.
Yeah. Thank you.
Evidence I gave. Yeah.
Okay. Anyone for any more, or are we all exhausted? Sorry, Diana, you were muted then, and I thought you said something, but
Yes, I'm afraid I have loads more questions, but where was I? There's evidence for a dormant volcano. Is there any other evidence for active cryovolcanism?
No, I really don't think there is at the moment. That's what I've read.
Okay.
I don't think there is, and I don't. I think people suspect that it must be happening because, clearly the chief component, a very significant internal component, is ice. And you would expect it, but it's not a case of Io where there are spewing volcanoes everywhere and it's completely clear. In fact, it isn't clear. There's one suspected. My understanding is that there is one suspected cryovolcano, but there's no smoking gun for cryovolcanism, a direct evidence. It's circumstantial evidence only, I think.
Right. Yeah. Thank you very much. Yeah, because I knew about the one, but I haven't followed it in years, so
No.
thought there might be an update.
No, but I'm not. I don't think there is an update, but I could look into it more.
Yeah, volcanoes are my thing. So.
Okay.
Right. There was one more. Oh yeah, the other question was about the crater count.
Oh yes.
Is what's the crater count like for Titan? I mean, is it closer to Mars or is it closer to Earth-like?
I think it's much closer to Earth-like. If you look at the global, if you look at the, shall I share my screen? Is that all right?
Sure.
Sure. Can I just go back to the?
Yeah, I think you'd indicated there were only a handful of
yes, that's right.
craters,
yes.
Which sort of indicated that if they were there before, they've been eroded a bit like most of them have been on Earth.
Yes, exactly. So there are two mechanisms that. So if you look here, Diana, there in this image, can you see it? So the red blotches are the known craters. This is a global map, despite the fact it looks like only one hemisphere, but it's a global map. So there are 1, 2, 3, 4, 5, 6. It's a bit like Wes Wally. I'm trying to find craters, but there are 6 that I can see in my 7. 1, 2, 3, 4, 5, 6, 7. I can see with my paw. 8. There you go. So 8.
It puts Titan actually between Earth and Io in terms of activity. Wow.
Yes. Okay. In terms of craters, you mean?
Yeah, in terms of the crater count. Wow.
Crater count, yeah. And it's because, as I mentioned, there are 2 effects. You've got the vast atmosphere, which is absorbing the energy of most objects, and then you've got the process of erosion, which tend to wear away and bury, and then of course you've got the limited. Well, actually, the coverage of the imaging, the coverage is pretty good. Actually, of course, it's amazing of the Cassini and emission, but nevertheless. There could well be craters we haven't discovered yet, because craters on a surface like Titan don't scream crater like they do on the surface of the Moon or Mimas, whose name I embarrassingly forgot in my presentation. I hope nobody noticed, but anyway, I've pointed it out to you, so it's too late.
We didn't notice, Brian.
You didn't notice.
No.
It was exceptionally difficult moment, that was.
And then the last was Ontario lacus there. I was also wondering if, given that it was summertime and it had a different composition and so on, and not connected, and et cetera, I was wondering if it's the Titan analog of like a salt lake, like the Dead Sea.
Well, that's a lovely idea, and I think that certainly rings true to me. I'm trying to remember what the flipping thing is now. Hang on, where the slide is now. So it's interesting. The lakes of Titan are affected by the seasons, and the reason why it's thought there are more lakes in the northern hemisphere is because from many of the observations, the northern hemisphere was in winter, and therefore the temperature was lower, and therefore there are more likely to be precipitation, and therefore it's thought that the lakes grow when the relevant hemisphere is in winter and evaporate when it's in summer. It's a very gradual process, so it's not as if it's not thought that the lakes all disappear in summer and all reappear in winter. And because, let me see, the north, I think, was going into autumn, and the southern hemisphere was going into summer at the time. So there is evidence of evaporation, I think, from Ontario Lake, because there have been images taken over a period of time to see that the edges of it evaporating. I think it's Ontario Lacus. So definitely the lakes are influenced by the seasons, as you would expect, because of temperature variations. And so it's quite dynamic in that sense. But the seasons are driven chiefly by the orbit of Saturn around the Sun, and not the orbit of Titan around Saturn, because the axial tilt of Titan and Saturn is the same or very close. It's 27 degrees. And there are other seasonal change effects as well, such as the storms that occur at the equinoxes that cause the downdraft of winds, and winds of stronger winds, which can cause are thought to cause the formation of the dunes, which would otherwise be quite inexplicable without those seasonal changes.
Thank you so much.
That's all right. It's nice to have lots of questions. And until you get ones you can't answer, then it's not so nice.
That's when the fun starts.
Yes, indeed. But it's good to have the discussion. No one has a monopoly on anything. So
yeah. I just love the idea of like salt lakes on Titan.
Yes, absolutely. Yes. It's lovely that it's huge and very shallow. I mean, imagine standing on Titan and looking at it. It would be like a vast mirror. I don't know how transparent, actually. In my mind, hydrocarbons are opaque, like tar, like petrol. Well, I suppose petrol is semi-translucent. But if it had some translucent properties, you could get some very interesting effects, optical effects.
I always think of it with all the methane, and so I think of it as being bright blue.
Oh, okay. Is methane bright blue? Liquid methane? Maybe it is.
Neptune.
Oh, I see. Okay. Yeah, of course. But I think the blueness is a mystery at Neptune, isn't it? It's not. It is, or is it caused by the methane? I thought it was a bit of a mystery. What the colour? Because
it was mostly methane rain.
Oh, okay. Because methane on the Earth at standard temperature and pressure is transparent. It's not blue.
Okay. Well, maybe I'm wrong.
No, I'm not saying you're wrong. I'm just saying, I'm not saying you're wrong. That could well be. I know that Neptune has a lot of methane, and it may well be at those temperatures. It is blue, but I just happen to know that methane at standard temperature and pressure is colourless. But I'm sure you're right.
Then there's all that orange hue, isn't there, in the atmosphere? So
of Neptune or Titan?
Of Titan.
Titan. So that's caused by the thiolin.
Because of the fog or smog or whatever you call it.
It's the smog. I think of it as smog because it's orange, of course. And when we think of smogs, we think of orange. So the thiolins are formed lower in the atmosphere as the molecules become more and more complex. And the thiolins are definitely very, very complicated molecules that can also be synthesized on the Earth, and have been by Carl Sagan, and before him Miller and Urey, the Miller-Urey experiments, where basically they took a mixture of the sort of molecules you'd find on the early Earth and also on Titan, so not oxygen but methane and nitrogen, and apply an electrical discharge to them, and this produces a tar basically of a whole range of organic molecules, some of which are even amino acids. So I don't know whether the thiolins on Titan are thought to be amino acids, but because the molecules are so complicated, although that you can get instruments that detect the spectra, and you can get instruments that detect how many Daltons a given molecule has, it's much more difficult to actually get the structure of a particular molecule when it's very large. And I think for many of the molecules in thiolin, it is a bit of a mystery, because thiolin is not a particular class of compound. It's basically a nickname for a group of a whole swathe of molecules whose molecular structure we don't properly know, because they're extremely difficult to establish.
Can I ask you a hypothetical question, Brian?
Please do, Mark.
Yeah, with this, you kept going on about the size of the spacecraft. Do you think building it on the moon and then sending it would be a lot advantage to us? Because it's the payload. You were saying it's too small, so going away to a long distance, they'll be able to build a bigger ship, or a better spacecraft to do that.
This is the sort of thing I talk about at work all the time, because I work for SSTL, and we build spacecraft, and we're always talking about what we could do. You know, the great advantage of the moon, of course, is that it has a lower surface. But the vast disadvantage, which trumps that, is, of course, that all the energy and all the effort you need to get to the moon to transport the materials, some of the materials at least, to the moon, or you'd have to mine them from the moon. People talk about these things as if they're straightforward, and of course they're not straightforward at all, requiring vast amounts of energy and expertise to transport them from the Earth, if that were the technique. But to mine anything has never yet been demonstrated, and although conceivable, is certainly not possible until you've built a great deal of infrastructure, and never mind all the extra infrastructure, such as the machinery and the clean rooms and all the energy that you need. So it's a very complicated question.
Well, I mean, transport up in little loads, and then assembling it up on the moon, and then sending it off.
Yeah, but I think actually, I think that a really plausible. I think a plausible proposal is to do it in orbit. In fact, it's actually rather easier in some way. If you're going to bring your stuff from the Earth, my choice would be to do it in orbit.
Yeah, like the ISS.
Yes, indeed, because we've demonstrated the ISS, so we have the technology. And in fact, interestingly, the program to the moon, the Artemis program to the moon, of which I'm working on one of the spacecraft for that at the moment, an orbiter. But the part of the Artemis program is a International Space Station equivalent for the moon. So there is a plan to build an International Space Station, but for the moon, and to use that to dock spacecraft with, and then to go to the moon surface subsequently, rather than doing it in a single shot. But not all the space industry agree, and there's a bit of a tussle at the moment as to how best to do it. So I think the first people on the moon will go there in a sort of an Apollo way, by going directly to the moon and then coming back to Earth. But subsequently, the plan is definitely to build a more permanent infrastructure, and to start with not an infrastructure on the moon, but an orbiting one, because in some ways it's easier to assemble things in orbit than it is on the surface of an object. And remember, it's still fraught with problems landing on the surface of another world.
It's just travelling as well, because you need to build tanks big enough to put the fuel to take you there, because it's such a vast distance.
It is, yeah.
I think the other thing, Brian, is although it's easier maybe to think about launching something from the moon with lower gravity, you mentioned that half the fuel was taken up in slowing it down when it gets to the other end.
Yes,
and you've still got to have that same amount of fuel whether you launch from here or the moon.
Yes, indeed, you do, because it doesn't eliminate the need to brake at the Saturn. Absolutely. So it's a wonderful idea. I think we will eventually build infrastructure on the moon, but I think that will be, it'll be quite a gap between that process and then going on to build spacecraft and launch things from the moon. But obviously, there has to be some launch capability to go locally. Otherwise, you wouldn't be able to, otherwise it's a one-way trip to the moon, and nobody wants that. Yeah, it's a fascinating subject. The British Interplanetary Society have come up with Project Daedalus to go to Jupiter and then to sample the atmosphere of Jupiter as a source of energy and fuel to go to the nearest star. These are the sort of interesting things the British Interplanetary Society get to work on.
Thank you.
That's all right, Mark. I'm not sure I answered your question very well.
That's all right. Just quite interested in it.
Yeah, it is fascinating, and it's not ludicrous.
They want to build something on the moon, don't they?
Absolutely, but it's not a zero. It's not. All the advantages are not one way. That's the only thing. It's a very, very mixed picture. It's not just advantages, it's disadvantages, one has to think about as well. But certainly the moon is asking for us to do something with it.
Okay,
May I ask a question?
Please do, yeah.
Yeah.
Sorry, it's just the craters again. Now, there was some research published quite a while ago about the depth of the craters on Titan being hundreds of meters shallower than similar sized craters on Ganymede. So suggesting that there was some kind of process that was filling the craters on Titan. Any idea what that might be?
Well, I think first of all, no, I haven't read the article, so I'm sort of thinking on my feet here. But first of all, the velocity of any impacts would lessened, and the erosion of the atmosphere is very substantial on Titan. On Ganymede, there's virtually no atmosphere at all to speak of. Nothing that could really break something substantial. So if you take the same objects that created the very massive craters on Ganymede, the same objects traveling at a comparable velocity, kinetic energy, if you like, would be unlikely to have the same impact on Titan. So the crater itself would have a different profile and would be likely to be shallower. That's my intuition. So to begin with, it would be shallower anyway. So you're not comparing like with like. And in addition, there are processes, we know there is liquid on the surface, and there is likely also, as we discussed before, to be the transport of solids with those liquids. But how catastrophic that is, and how sudden it would be, and the liquid, the standing bodies of liquid are in the polar regions. So if the crater appeared in the equatorial regions, you wouldn't expect there to be substantial surface liquid to fill in the crater, but it is thought that there is subsurface methane, liquid methane under the surface. So we have aquifers on Earth where we have subsurface liquids, but there's also thought to be the equivalent methanifers, rather wonderful name, under the surface of Titan. So I would imagine that there could easily be, for a large crater, liquid and solid transport inside that crater. But of course, there'll be a random element as well. So I would expect sometimes that would occur and sometimes not. So whether there is still a residual mystery as to why no craters appear to be anything like that depth, as far as I know on Titan, I'm not sure. But don't forget also that Titan has a global subsurface ocean. Indeed, Ganymede may do as well. But it has quite soft, icy layers too. So that could also fill in, those deeper layers could also fill in the crater as well, if you see what I mean, not just the methanifers of liquid methane, but also the ice. But I'm slightly thinking on my feet there because I haven't read the article.
Okay, thank you.
That's all right, but there are mitigating circumstances which would make craters either not that deep in the first place or cause them to fill in. I think there would be, yeah.
Okay, are there any more, or shall we draw this part to a close, give Brian's voice a chance to recover. I realise you've been at it for quite a long time, Brian. So
I've loved it, actually.
again,
I've really loved it.
Really appreciate your time.
That's a pleasure.
Can I suggest that we show our appreciation in either the audible or the virtual reactions method? So thank you, Brian.
Yeah, thank you, Brian. Cheers, mate.
Right.
Yeah, well done.
Thank you very much.
you.
Thank you very much. I'm sorry about the embarrassing moment. I forgot Mimus, but apart from that,
That's
hopefully
okay.
it wasn't too bad.
Easy to forget the Death Star.
I just looked at it and thought, I don't remember the name of this body. Anyway, if you cut out the embarrassing bit, can you cut out the embarrassing bits from the recording?
Yeah, I'll see
That'd
if I see what I can do to edit the recording.
That'd be good. Yeah, just say Mimus when in your voice when I couldn't remember it.
Which reminds me, I'll stop the recording at this point.
Okay.